All right, so let us start with the actual physics. So the previous videos were introductory videos. So as promised, the first topic is topic 5, further mechanics. And sorry, I already warned you that my handwriting is not perfect, and I also have a slight accent, as you can imagine, maybe a heavy accent. Hopefully it's comprehensible. So I like to start most of my physics classes with a quick recap of measurements and units and such, because physics is all about taking measurements. So if you take measurements, you need base units and an understanding of what you are measuring. So base units help you understand what you're measuring. So in physics, there are 7 base units. So the base units in physics are 7 independent units. And what we mean by independent is that, for example, mass cannot be expressed in units of length, and length cannot be expressed in units of seconds, and so on and so forth. So these 7 units are the following. First one is mass. The base unit is the kilogram, okay? And the kilogram is the only base unit that has the prefix of K, which means 1000, and it's 1000 grams, okay? I'm gonna talk about prefixes later. So the next one is distance, is measured in meters. The next one is time, measured in seconds. The next one is current, and it's measured in amperes. Okay, so this is how we write ampere. And 1 ampere is 1 coulomb times second. This is a point of confusion for some students because they think that coulomb is the base unit, but it's not. It's actually current. Okay, the next one is temperature, is measured in kelvins. The next one is amount of a substance. And we will actually need this when we talk about nuclear physics, okay? But amount of a substance is mostly used in chemistry. The amount of a substance is measured in moles. And the last one, which is rarely used, honestly, I used it only once in my life, and I've taken billions of physics classes, so I never really used it. The next one is, and the final one, is the luminous intensity. The unit is CD, and it means candela or candela. All right, so as I mentioned already, independent means, let's write it down so you have it. Independent means, independent means that no base unit can be written in terms of any other base unit. So mass is independent of time. Time is independent of current. Etc. So this is similar to the XYZ coordinates. So the X coordinate Like if you take the unit vector along the x-axis, that one cannot be expressed in terms of the unit vector in terms of the unit vector in the y direction, for example, okay? Anyway, using these 7 base units, so using these 7 base units, we can define all other units. So units that are derived from these base units are called derived units. So these are called derived units. Okay, so some of these derived units have special names. So for example, force, which is given by mass times acceleration, is measured in newtons, and 1 Newton is 1 kilogram times 1 meter per second squared. Another unit that has a special name is the joule, which expresses energy. So for example, kinetic energy is 1/2 mv squared, and 1 joule is 1 kilogram times 1 meter squared over second squared, which you can see from here. So mass is in kilograms and velocity is in meters per second. So velocity squared is meter squared second squared. So the joule and the newton are derived units. And of course, other popular derived units used in physics are the units for velocity. So velocity is distance per time. So it's expressed in meters per second. And then acceleration is velocity per time. So it's meters per second times 1/second. So meters per second square, right? Now, the rules for working with units. So working with units rules. So kinetic energy, for example, is 1/2 mv squared. So in university physics, you usually put square brackets like that to express the units for a given quantity, okay? So if you put everything in square brackets like that, and this is not something you should do during your test, this is just demonstration, okay? In the test, you just write it down. So for example, kinetic energy, this means the units for kinetic energy, which is joules. This means the units for 1/2, which is 1, because this is a constant and constants don't have units. It's just numbers, okay? So 1 joule is, okay, this has the unit 1. It's dimensionless, as we say. Mass has units of kilograms. Velocity has units of meters per second. So if we square it, we get meters squared per second squared. Another thing you can do, which I just thought about, is the following. For example, force is mass times acceleration. As I said, you don't really need to use square brackets, as I just showed, but you can just directly write down the units. So if we solve for acceleration, we see that acceleration is force per mass, right? So we just saw earlier that acceleration is given in meters per second squared. So this must be equal to, what are the units for force? Newtons. What are the units for mass? Kilograms. So meters per second squared is equivalent to newtons per kilogram. So simple as that, okay? So you can kind of work with units like that, like you can solve for units. And similarly, you can do the following. For example, kinetic energy is 1/2 mv squared. if we solve for v squared, we find v squared is kinetic energy over 2 times kinetic energy over mass. Okay, so meters squared per second squared is equivalent to joules per kilogram. And notice that this is not equal to 2 times joules per kilogram because 2 is a constant. So constants don't have dimension. So we just kind of delete that and we are left with the units. So meters per second squared are equivalent to joules per kilogram. It's not a popular unit, but this is something you can play with. All right. This is actually used, as we will see, when you work with gravity. The Newton per kilogram is used to express acceleration, actually. So let's talk a little bit about prefixes. So when you have to express, so if you want to express large or small quantities, you use prefixes in front of your base units or your derived units, okay? So 10 to the third is called kilo, okay? Kilo. 10 to the sixth is called mega. So for example, 1 megajoule is 10 to the 6, 1 million joules, okay? 10 to the 9 is the giga, okay? Giga. And then 10 to the 12 is the tera, okay? You can go beyond that. It's rarely needed at the A-level physics level, so I'm not gonna go beyond that. And now for small quantities, you have 10 to the minus 2 is the famous, I wanted to say, centi. So 1 centimeter is 10 to the minus 2 meters or 0.01 meters, okay? 10 to the negative 3 is the milli. 10 to the minus 6 is the micro. 10 to the minus 9 is the nano. 10 to the minus 12 is the pico. So this is an n, by the way, and this is a p. So this is pico. And 10 to the negative 15 is the femto, okay? So as you will see, we will need 10 to the negative 15 actually, because 1 femtometer is about the radius of 1 proton or a nucleus. So it's as small as that, okay? So let's divide this. Okay, so this is for large and this is for small quantities. Some things to pay attention to is that 1 kilojoule, okay, is 1000 joules. Okay, that's simple. But 1 milligram is 10 to the negative 6 kilograms. Okay, be careful with when you use kilograms because 1 gram is 10 to the negative 3 kilograms. Okay, because why is that? Because you have 10 to the negative 3 from here. Actually, let me use red. So 10 to the negative 3 times 10 to the 3 cancels each other. You get 1. So 1 gram is 1 gram, okay, which is doesn't make sense. But you have to remember that 1 gram is 10 to the negative 3 kilograms, okay? Because kilograms is the only base unit that comes with a prefix, okay? So be careful when you work with kilograms. All right, so another thing we will need in physics is scalar and vector quantities, okay? So scalar quantities only have magnitude, but no direction. So time is a scalar quantity. It's measured in seconds, so 10 seconds you don't need to specify a direction for time because seconds is enough, okay? It's a scalar quantity. Same goes for mass. If something is 10 kilograms, the concept of a direction for a mass doesn't make any sense, okay? So these are scalar quantities. These are numbers expressed with base units or other units because energy is also a scalar. It's measured in joules, which is a derived quantities. So actually, let me write this down. So examples of scalars are mass, time, distance, and energy. Okay, there are others. This is not an exhaustive list, okay? So you can come up with other units as well. And then vectors are things, quantities, okay, that have both magnitude and direction. So for these quantities, you need to specify a direction. So let's say that I'm traveling with velocity 10 kilometers per hour. In which direction, okay? Don't confuse it with speed. Speed, I didn't write it down. Speed is a scalar. So speed is just the magnitude of the velocity. But when you talk about velocity, you need to specify the direction. So I'm traveling with 100 kilometers per hour northwest or southwest or just north or west, etc. Okay. So for vector quantities, you need to specify the direction. So other examples could be force, momentum, acceleration. So all these quantities need to be specified by their direction. So for example, acceleration, if an acceleration is negative, it means that we have deceleration. So when we press the brakes, when we apply the brakes in our car, then we get deceleration. So that comes with a negative sign, for example, okay? So I'm gonna write them down: velocity, acceleration, force, and momentum. And I think I'm gonna stop the video here. I'm gonna name it quick recap, and it's gonna be the first, like the 0th video in unit 4, okay? Because you kind of use these concepts a lot. So this is still not part of unit 4, I'm sorry. We will start with momentum in the next video.